All right, can you hear me? Yes? Okay. About way back there. Uh-oh, can't hear me back there. Can you hear me? Oh, okay. All right. Oh, this might help if I plug it in. Yes, okay. All right. Here we are again, one more time. Probably another 20 or so. Let's see. Lab 3 demo is due tomorrow. Homework 3 due Wednesday, and we have a midterm coming up on Friday. Midterm will be here, 65 minutes, covering everything up to and including homework 3. Are we ready? I'm not sure we're ready. Are you ready? Yes? Okay. All right. Let's see. In Canvas, I just want to make sure everybody knows that there are homework solutions, lecture slides, and sample exam. Okay, any questions? So I'm not sure we're going to get homework 2 graded back before homework 3's. So make sure you look at the solutions. Okay, so this is where we are. One person has turned in homework 3, yay. And homework 2 is only 6% graded at this point. Okay. Any questions before we launch into today's fascinating topic?
I feel less bad about procrastinating on homework 3 until today, knowing that everyone else has done the same.
Well, you still have more than 2 days. It's not.
Oh, it's not due tonight?
It's not due tonight?
No, it's due Wednesday night.
Due tomorrow.
Today's not Wednesday. It's Monday. Okay. Wrong mistake. Anyway, continue.
Any other questions? We're good. Okay. All right. So on Friday, we talked about analyzing sequential systems, right? Our sequential systems are vanilla. They have flip-flops, and they have combinational logic, and they're always structured so that the combinational logic takes the inputs, the present states, and generates outputs and next states. Did you have a question? No? Okay. All right, so we looked at also how to generate a counter. We already knew how to build a counter, but we synthesized a counter assuming we didn't know anything about the patterns that a counter uses. Okay, so let's do some more. So here's our first example of designing a sequential system. So these are word problems. We have some kind of specification of what we want to happen, the behavior of our circuit, and it could be given in a natural language, which is always problematic, or maybe some equations. That's usually more helpful. Okay, so here we're asked to design a sequential circuit called even block. It's going to have one synchronous input and one synchronous output. Okay, so from this, I know that its a component block, its symbol block, is going to look like this. It has one input X, and then it has a clock input, because if we said synchronous input, it means we're going to provide you a clock to tell you when to sample that input, and one output y. And so this is going to be a synchronous system. And now we need some kind of direction as to what it's going to do. And so here's the English description of what it does. And sometimes this is a little ambiguous. It's always fair to go back and ask questions and make sure you understand what's expected. Okay. The description says the output should be 1 for a whole clock cycle after, very important word, after, that's why it's in red and bold. You have an even length block of 1s followed by a 0. So you need an even length block of 1s followed by a 0 on the input in order for the output to be 1. Okay, so usually there's going to be a sample input because this is very instructive. So for example, here are inputs X and output Y at the various clock edges. So just at the clock edges. And you can see that X has 3 1s here. 3 is not even. So Y doesn't do anything. And now we have 0 followed by 2 1s. 2 is an even number. And then we have a 0. And after this 0 is clocked in, then we get a 1 on the output. Okay? All right, and it's only 1 once. All right, every time we have an even block of 1s followed by a 0, we're going to output a 1 on the following clock edge. So we actually have to clock in this 0 before we're going to respond. Okay, and let's see. So here's another block of 1s, and this one has 4 1s. 4 is also an even number, so Y is also 1 here. Okay, so now we have to, this has to be sequential, right? Because we have to keep track of what we saw on X. In particular, we need to keep track on how many 1s we saw. All right, so let's design. Our first task is to come up with a bubble diagram or state diagram. Yes?
If there were 2 zeros in a row, would that also count as an even amount of ones?
No, we don't care about the zeros. We just care about the 1s, right? It says an even length block of 1s. So the zeros are the purpose of the zeros here are to separate the blocks of 1s. In order to have a block of 1, you have to have a 0 before it and a 0 after it. Otherwise, you don't know where it starts and ends. Okay. All right. So the first state is always easy in these things. I used to call these idle, and then I think 5 years ago, the class decided it should be called chill. So we've been calling it chill now. Okay, so your state machine, your circuit wakes up, and it's in the chill state. Not doing anything. Hasn't got a clock edge. So this is our initial state. Okay, well, we haven't seen anything, so probably we should output a 0 because we really haven't seen anything at all, so we haven't seen the desired pattern. Okay, now what should we do on the next clock edge? Yes? Odd? So regardless of the input, I should no, okay. So all right, let's do this. Suppose the input on the next clock edge is 0. Okay, then that's not really interesting, right? I haven't made any progress. But if it's 1, what should I do? Yes.
Go to a state where you're listening for 1s and counting them.
Okay, so I should change state, right? I shouldn't stay put, because if I stay put, I'm going to forget that I saw 1. So I really need to change state. Okay. I change state. I'm going to call this one odd, because I need to keep track of whether I've seen an odd number of 1s or an even number of 1s in this particular case. I should still output 0, right? I haven't seen the pattern yet that I'm looking for. Okay. I could have called this Sally, but odd seems like a good name because we've seen 1, 1, and I need to keep track of odd and even. Okay. So what happens if I see another one?
Go to
Okay, I should leave, and then it should be even, right? So now I've seen 2 1s. Okay, what happens if I see another one?
you jump back to odd.
Okay, so as long as I'm seeing 1s, I'm going to bounce back and forth between odd and even. I don't actually need to know exactly how many 1s I've seen, just whether it's odd or even. Okay, and my state can keep track of that for me. Okay. What happens here? I don't see any change. Okay, suppose I'm in odd and I get a 0 though. I'm back to the start, right? That was an odd length block. I'm back to square 1. Okay. How about if I'm an even and I get a 0? I did, followed by a 0.
Is there another state for just outputting the
Yeah, I have to be in a state to output a 1, right? Because I want to output a 1 for a whole clock cycle, regardless of the input. And I want to output it after I clock in the 0. So I'm going to go to another state, and in that state, I'm going to output 1. Okay. So here I am. So Eureka, we found the pattern. So the only way to get from chill to Eureka is to see an even number of 1s followed by a 0. Okay. What happens if I get a 0 now? I go back to chill. Okay, how about if I get a 1?
go back to odd.
Okay, so here you need to be a little bit careful here. Your inclination might be, okay, you're going to start over because you found 1. But hey, you saw a 0, and now you have a 1. So that 1 could be part of another block. And so you want to go back to odd. Okay. Okay, there's one more thing I need to specify in my diagram for somebody, and that is what state I want to wake up in, which I think we already knew, which is chill, right? So sometimes you'll see this lightning bolt directed at a state, and that means that if you zap your circuit, if you reset it, you should wake up in that state, or that state is your initial state. Just like when you apply the global reset on the Basis 3 board, you want your circuit to wake up in its initial state. And all the flip-flops will go to 0, so hopefully that'll be your initial state. If that's not your initial state, you need to do something to make sure you wake up in your initial state. Okay. All right, so here's our state. So this is, the part that's for which we need you. I don't think ChatGPT can do this yet. Maybe someday, but we still need you. Okay, the rest of this is mechanical. We're teaching it to you so you understand what the tools do and what the process is. Okay, but, once you're here, you just follow the steps and you'll get to your circuit. Okay, so what are the steps? So from here, assuming this is correct, and that's often a big assumption, but assuming it's correct, we can generate the symbolic state transition table. Right? So we have a row for each state, and then we specify what the next state is, and that depends, of course, on the input, x. And so for each state, we list what the next state is when x is 1 and when x is 0. So for chill will go back to chill when x is 0, and it'll go to odd when x is 1. Okay, so we're just saying what are the at the end of the arcs for both values of x. And then we have the output for each state. So the output for each state is, they're all 0 except in Eureka where we output a 1. Right? Okay, so it's just a direct translation. Once we have that, then we need to encode our states in zeros and ones. And there are many ways to do this. I'd like to tell you it doesn't matter, but it does. How you choose your encoding can determine how big your logic is. Typically, in the past, we've always wanted to use what we call minimum length encodings, which means as few bits as possible. Here we have 4 different states. If I'm going to encode that as bit vectors, each state as a bit vector, how many bits do I need? 2, right? Always log base 2. If you have a number of states which is not a power of 2, you're going to have to go to the next highest. So if you have 3 states, you'll still need 2 bits. If you have 5, 6, 7, you'll still need 3 bits. If you have 13 states, you'll still need 4 bits. And then there'll be some values that you're not using. Okay, so we're going to pick the obvious 2 bits. This is a minimum length encoding. And we are going to make chill 0, 0, so that when those flip-flops wake up and I zap them with the global reset, they will be 0 and we will be in state chill. Okay. And then, the others I just did in a row, in order, doesn't matter. Okay. Now I have my encoded state table where I've replaced the encoding of each state with its bit vector. So chill, odd, even, or Eureka are in order 0, 1, 2, and 3. And then we just filled in the corresponding. So these both were chill. This is Eureka, which is 1, 1, chill. And then we have odd, which is 0, 1, and even, which is 1, 0. And then we have the output. Okay. All right. And now I need to get my logic. So I need to come up with equations for the outputs D1, D2, and Y. Okay. So how do I fill in? So this is a little bit tricky. There's some danger here because you have to make sure you get the right value in the right place. And this is affected by how you label your K-maps. Okay, I do it this way because I find it a lot easier to think of the columns as going into the rows of the K-map. So the way I do it is x is always the horizontal variable. Again, you can do it some other way and still get the problem correct. And then I have Q0, Q1 in order, 0 down. Okay, so when I look at the state transition table, I have my states going vertically down the rows, so they go horizontally across the K-map. And x is 0 is the top row, x is 1 is the bottom row. So this particular column goes here, right? It's the top row because that's the region where x is 0, and this is D1. Now, you have to be a little careful. These are in order 0, 1, 2, 3. So when you fill in your K-map, this is 0, 1, 2, 3. Okay? So here it mattered. If I get these backwards, I'm going to have a different function. Okay, so where does the next one go? Is that what you're going to say? Yeah, okay. Top of D0. Okay. How about the next one? Okay. And the last one, where does the last one go? Bottom of D0. Okay. All right. Some of these if you swap them, it doesn't matter because they have the same value, but some of them it will matter. So be careful with the fact that these last two columns are not in the same order as these rows. Okay. We can do the output here. You probably didn't need to do a K-map for the output. Nobody usually bothers with two variable K-maps, but just to be complete, there it is. Okay. When we do a Mealy machine, it will not be a two-variable K-map. It'll be a three-variable K-map. All right, so we've got our K-maps. We can draw our essential prime implicants, and here I didn't make a list of them because they're all forced, so you're going to need them all. And we can get our equations then for D1, D0, and Y. So these are the outputs of that combinational logic cloud, right? And then all I need to do is hook them up to the flip-flops, and I'm done. And now I have a sequential circuit that behaves exactly like or according to that spec. Okay, so there will be a problem on this, definitely on midterm 2 and the final, not on midterm 1. Because you haven't had a chance to practice, you'll get some homework problems to do first. One thing I want to mention is that if you fail to connect the clock, you will lose a point. Okay, there are too many times where someone in the lab will tell me their circuit's not working, it's not doing anything. And I'd say at least a quarter of the time it's because they left out the clock. Your flip-flops will not, did you do that already? Okay. If you have a sequential circuit with flip-flops, you must connect it to the clock. It will not do anything until you have a clock. Okay. Any questions? Oh, wait. You probably want to see the Verilog version of this. So this is what you would then enter to get this circuit in Vivado. You would create a module called even block. It has input X and the clock as an input, needs the clock, and output Y. You can only connect the clock to the flip-flops, right? That's one of our rules. Here I've made a bus for the D inputs and the Q outputs of the flip-flops. So you're going to have possibly some state machines with, 5, maybe 8, 9 flip-flops. So you're going to want to make a bus. You're not going to want to use individual wires. And you'll see that, in fact, we can make a bus of flip-flops. So you don't have to actually make instantiate a separate flip-flop for each one. Okay, so these are just the equations that we came up with. And there's why I used a reduction operator instead of ANDing Q0 and Q1. And so this is exactly this circuit. If we were to enter this in Vivado and ask it to produce a schematic, it would look somewhat like this. Okay. And here's our simulation. So we see it wake up and chill. X is 0. It stays in chill. X is 1. It goes to odd, and it bounces between odd and even. X, if we're in even and X is 0, then we go to Eureka. So it isn't until the clock edge after we clock in the 0 that the output will be 1. So the output is 1 on this clock edge. The Y will go high while you're in Eureka, but it's not 1 on the clock edge that drove you into Eureka. It's 1 on the following clock edge. while you're in Eureka. Okay. All right, so let's change this a bit. We're going to do version 2 of even blocks. In this case, we're going to have the same inputs and outputs, but we changed the description with just a slight word. And that is, we want the output to be 1 when the current input is 0. And we have seen a block of 1s, an even length block of 1s. So now we want to react right away. We don't want to wait till we clock in the 0, but as soon as x goes low after an even block of 1s, we should respond. Okay, so to show you the difference, right, this is the second version, y2. This is an odd block of 1s, so neither y nor y2 cares about that. Here's our first even block of 1s. y2 will be high on the same clock edge as the 0, whereas our previous one would have to wait till we actually clocked in the 0, change to state Eureka, and then output a 1. Okay, so this one is going to be a mealy output. It depends on the current value of x. Okay. All right, so our state machine looks similar. Here it is. The only difference is that instead of Eureka, instead of going to Eureka when x is low and I'm in even, I immediately output the 1. So I don't wait till I'm in state Eureka. While I'm in even 2, if x is 0, the output will be 1. Okay, and we can then go back to chill. Okay. All right. So if we go through the design here, I have 3 states now. In general, a Mealy machine could have fewer states in them more. Okay. So here are my 3 states, and now my output has 2 columns, right? Because when I'm in even 2, the output depends on whether x is 0 or x is 1. The other 2 states, it's still 0, both cases, but in even 2, I need to know what value x has. Okay, and we'll use the same encoding. And now I can fill in my state transition table. And there's one encoding I'm not using. I have 3 states, so I still need to use 2 bits. But I'm not using 1, 1. 1, 1 is not one of my states, which means that I don't care what D1 and D0 and the output are if both Q1 and Q0 are 1. Now, hopefully I didn't make a mistake in my logic, because if somehow they both become 1, I'm in trouble. But assuming that there's no error, I should never be in state 1, 1. Okay, and that's why these are don't cares. Any questions on this? Don't cares. Okay, all right. So we're going through the same process again. Now I need to get logic for D1, D0, and the output Y2. And now they're all 3 variable K-maps, because now Y depends on X. Okay, but we have a don't care. Right, we have, when both Q1 and Q0 are 1, we have don't cares. And so my logic is actually a bit simpler, too. There it is. Okay. Yes?
What would it look like if you did this
Added a flip-flop.
A delay, yeah, flip-flop.
I add a flip-flop, so that's what we call a synchronized Mealy machine, and it's technically a Moore machine, right? Because now the output only depends on the flip-flops. So that is a technique. It would then be equivalent to the original one. But I used 3 flip-flops, right? And I could have done it with 2.
Less logic.
But less logic, yeah. So there are trade-offs here. Yes. And not only that, but the state encoding you pick, that affects your logic too. Okay. We're not going to ask you to try all different encodings. There's way too many to try. And when we give you a problem to do on the homework or on an exam, we will give you which state encoding to use because we don't want to check 20 different versions. Okay. There is research on actually trying to identify which state encoding gets you the best logic. Yes?
Are there many others besides Moore and Mealy?
No, Moore and Mealy are the 2, right? Either your output depends on the input or it doesn't, right? Okay. All right, so just to show you the difference between the 2 on the same input, they would both start in their chill states and they would both bounce between odd and even. The difference is that the Moore version is going to go to Eureka, whereas the Mealy one is going to go back to chill. Right? The other difference, of course, is that here we're getting an output of 1 earlier than here. So Y2 is 1 on this clock edge, whereas Y is only 1 on this clock edge. So our output is delayed. But we wanted a nice pulse on our output. The advantage here is that since that Y will be 1 for one entire clock cycle, whereas Y2 will go up and down as X changes. So while X is changing here, Y is also following X. And so any kind of change on X here will be reflected on Y2. Yes?
And is the reason that it's shifted a little bit to the right of X because there's some kind of delay? Or
Yeah, there's that. We actually had to clock in the 0 before we reacted, whereas the Y2 is reacting immediately to changes in X. Right? So they're not equivalent. These are 2 different machines. They don't have exactly the same output. Okay, one of them is reacting immediately. The other one actually has to wait for the input X to be clocked in to react. Okay. All right. So I have one more example. Okay. And this one has 2 inputs in addition to the clock. Okay, so this is a small example. So it's hard to come up with really small examples. And if I get something realistic, it's going to have too many inputs and flip-flops to actually deal with it with K-maps, which you probably think is a good thing. But in about 10 minutes, we'll show you how to not deal with K-maps at all. So something to look forward to. All right, but let's first do this the conventional way. All right, so this is a little component called message check. And the idea is you're receiving messages 1 bit at a time. And the message is coming in on the D input. So, but you're not always receiving messages. Sometimes there's gaps between messages. There's idle times between messages. So how do you know when a data bit is part of a message or it's just garbage in between messages? Well, that's where the S bit comes in. So the value of a message bit, whether it's 0 or 1, is on D, but the S input marks when the message starts and when it ends. So it's a start bit and a stop bit. And so until you get S being 1, you can ignore D. But once S is 1, you got to pay attention to D. And then when S is 1 again, that's the last D you need. After that, you can, again, ignore D. Okay, so those are the two inputs you receive. And the job of this little component, message check, is 1, to tell the world when a message has been received. So when S is 1 at the end of a message, E should be 1, saying this is the end of the message. This is the last bit of a message. And then we have an output P, which is doing some check or parity check, or not quite parity, but it's doing some error checking for us. Because all of our messages are supposed to have a number of 1s, that is 2 mod 3. Okay, 2 mod 3 is just a complicated way of saying that the number adds up to a multiple of 3 plus 2. So that would be 2, 5, 8, 11, 14, 17, 20. Any integer that happens to be a multiple of 3 plus 2. Right, so 60 is a multiple of 3, so 62 would be 2 mod 3. Okay. All right, so just to make sure we understand what's going on here, here's a sample input and output. So S is 1 at clock edge 2, and again at clock edge 6. So our first message is 5 bits. Our first message is 11001. Our second message starts at 8 and ends at 9. So each message has to have at least 2 bits, right? And this is about as short as they can get. So this message is just 1, 1. And the next message starts at 11 and ends at 13. And then there's one more that starts at 16 and ends at 20. So the bits on clock edges 1, 7, 10, 14, and 15 can be ignored. They're not part of messages. All right, so E will just be 1 when S is the end of a message. All right, so that's at 6, 9, 13, and 20. And now we need to count how many 1s were in our messages and check that they were 2 mod 3. So the first message has how many 1s? 3. Okay, so that's not 2 mod 3, so that's a 0. So something went wrong there. This one has 2, so we can output a 1. This one also has 2 1s, so we output a 1. And this one has, again, only 1 1. So we output a 0. Okay? So this is the component we need to build. We need to figure out how to output E and S. Sorry, E and P, not S. Okay. Right? So first message, E will be 1 at 6 and P will be 0. Second message is correct. Third message also was 2 mod 3. The fourth message was not. All right. Let's build this state machine. Okay, so what's my first state? Yes.
I'll answer the easy one. Chill.
Very good. Okay, chill. So we always start somewhere, right? And now I need to pay attention to 2 inputs. So now I'm going to write expressions on the arcs. Okay, so when S is 0, I don't care what D is. So this represents both cases when S is 0. So 0, 0, and 0, 1. Right? I'm just going to stay in chill because I haven't started a message. But if S is 1, then I have a message. And now I need to pay attention to D, because now I need to keep track of how many ones. Just like in even blocks, we need to keep track of how many ones we've seen. So I'm definitely going to want to go to 2 different states depending on what D is. Okay. So in fact, what's going to happen is I'm going to keep track, once S is 1, I'm going to keep track of how many ones I've seen. And now it's a multiple of 3. So here I've seen 0 ones. Then if I see one more, I've seen 1 1. If I see one more, I've seen 2 ones. And if I see another one, well, that was a multiple of 3, so I'm going back to 0. Right? So this is like a little counter, but we forget multiples of 3. So you just count 0, 1, 2, 0, 1, 2, 0, 1, 2. Okay, and we're going to keep doing this as long as S is 0, because we're in the message now. If we went over here, it's because S was 1 and we started a message, and now we're processing the message. Okay. While I'm processing the message, both of my outputs will be 0. Right? My outputs here depend immediately on the inputs. This is a Mealy machine. So all of these arcs are just going to output 0 because I haven't seen the end of a message. It's only the end of the message where I might need to output a 1. So I can just now we're going to look at the final arcs. These are the arcs when we hit the end of a message. And this is a little bit complicated because it depends on what state we were in. All right, so let's start with 0. So if I've seen 0 ones and S is 1, then I'm going to go back to chill, and E is going to be 1 because this is the end of a message. But I know that the output will be 0, and it doesn't matter what D is. If currently I have 0 ones, there's no way for me to get to 2 ones. Even if D is 1, I'm not going to get 2 ones. Okay. If I'm at 1, though, 2 different things could happen. If D is 0, then P will be 0 because I will not be at 2 ones. But if D is 1, 1 plus 1 is 2, and so E should be 1. Sorry, P should be 1. Okay, and then over here at 2, P should be 1 if D is 0, but if D is 1, then I'm going to go past 2 back to 0, and so this is also 0. All right, so there's a lot of details to get right here. Okay, but assuming this is correct, again, we have 4 states. That's convenient because then I can use only 2 bits. And now I have a much wider table because there are 4 different possible input values. I have 2 physical inputs, S and D, and together they can take on 4 different values. So I need 4 different columns. And same for the output. Okay, now a lot of these are zeros. As long as I'm in between a message, I don't care. My outputs, I mean, I do care, but my output's going to be 0. Okay. And we can do this. We can fill in. Okay. And then, of course, I'm going to punt, actually, to a web page that you'll have a link to. So this is the state machine. These are called R0, R1, and R2 to keep them short, but they're the same 4 states you had before.
Are you looking at the links?
Am I?
Are you looking at the link's contents or the
I am. Oh, what?
putting this into our own devices?
How's that?
That is lovely.
I'm glad you mentioned it. Because it's right here. Oh. It didn't, the power, that was not good. Okay.
Unfortunately, clicking on the PowerPoint again does cover up the shiny new browser, so.
I'll have it in my browser. Okay, there you are. Okay,
Yay!
you're
Thank
back. Actually, make it a little bit bigger. Okay, so there's actually a link to this from Lab 4, where you're going to be doing a state machine. Okay, so this is exactly the example we just talked about. And from those K-maps, you can get these lovely equations. Okay, what fun. And you can write the following Verilog for it. Okay, so in this case, the equations are in a separate module. They don't need to be. I could have just put them up here. Okay, the reason I do that is so that when you go to look at your schematic in Vivado, all your logic is stuffed into a module. Otherwise, it's all around the flip-flops, and it's hard to see what's what. But basically, this is what you get from the schematic in Verilog. Okay, so this works fine. However, we're going to suggest that you do something else when you do your state machines in the lab. So for the labs, you're going to have more than 4 states. So we're talking about at least 3 state bits, if not more, if you were to do a minimum length encoding. You're going to have many inputs, much more than just 2. So using K-maps is not going to be an option. Moreover, it turns out that there's a better way for FPGAs to encode states, and it's called one-hot. Instead of using a minimum length encoding, instead of using the minimum number, we're going to try to actually use what I consider the maximum number of flip-flops or bit vectors. Basically, if you have 4 states like this, you're going to use 4 bits. And the encoding will have only 1 bit that's high in each state encoding. So in state start, Q0 will be high. In state R0, Q1 will be high. In state R1, Q2 will be the only high bit. And in state R2, Q3 will be the only high bit. And this will make it a whole lot easier to come up with your equations because you can just read them off your state diagram. You don't have to put your logic in K-maps and circle prime implicants or anything. You can actually just read off what the actually, could I do that? Okay. All right. So, in fact, well, all right. So these are the one-hot state equations. Okay, this state encoding is called one-hot. And this is what you'll want to use in the labs. Here's the same code, except we're doing one-hot. Now, there's something interesting here. I don't know if you noticed, but this instance name is actually a bus. It's not a single identifier. And so that lets us declare a bus of flip-flops. So what this does is it makes flip-flop 1, 2, 3 with this name. And what we're going to do then is feed it a bus of length 3 that has the clock, a bus of 3 bits of 1 for the clock enable. Oh, I forgot the reset. Oh well, I should fix that. 3 bits of 0 for the reset. And then for the D inputs, D will be a bus and Q will be a bus. Okay. And then here are my equations. Now, you might ask, hey, why didn't I make a bus of length 4? Somebody want to ask that? Yes.
Why didn't you make a bus of length?
I'm glad you asked. Well, so one of the important things, vital things in, in one hot is to make sure that one of your flip-flops wakes up with a 1. If all of your flip-flops are 0, then all of these equations will always evaluate to 0 because they have product terms that involve a state bit. So if your state bits are always 0, your next state will always be 0. And that makes for a really boring state machine that never does anything. Yes?
Why couldn't you just initialize the input bus to, instead of using the duplicate modifier, just 1, 0, 0, 0 in the curve?
No, so init only works on, unfortunately, only as a additional, something that affects the library. It's not part of Verilog, so you're only initializing single flip-flops. So all of these have to be initialized to the same value.
Gotcha.
I can't put 1, 0, 0, 0, 0. That would be nice, but that doesn't work. So I actually have to separate one of them out and make that one initialized to 1. Okay? Yes?
Can we later connect the flip-flops into a larger bus for our own convenience with other methods like wires?
Sure.
Will it act?
Well, here are your D's and Q's. And you can refer to the D's and Q's the way you would if they were separate.
Gotcha.
Okay, let me go back to the PowerPoint. All right, so let's talk about one hot for a minute. So one hot is a state encoding where each state has its private bit. And so by just looking at a bit, you can tell whether you're in that state or not. Okay? So if you have n plus 1 states, you will have n plus 1 bits. Okay, so how do you come up with the logic? So let's say that I want to come up, each one of these bits is going to be held by a flip-flop. And I want to know, when is the next state going to be Q23? When am I going to go to state 23? Well, to be in state 23, I have to come in through an arc that goes into state 23. So here I have state 23, and I have 3 arcs going into state 23. One that's from 23, and 2 others, one from 13 and one from state 7. So to write the logic for the next state for bit 23, all I have to do is say, okay, I want to go to state 23. If I'm in state 23 and I have A or B, or if I am in state 13 and I have C and D, or if I'm in state 7 and I have this expression is true. And that's your next state equation. Right, so you can read them immediately off the state diagram. Don't have to make a table. Don't have to make K-maps. Okay, so the state diagram is even more important. Getting the state diagram will be the hard part. Correct will be the hard part of these labs. Okay. All right, so the state equations here, where were they? Right, we would look at, when do I want to go to chill? I want to go to chill when I'm in here and S is 1, or I'm in 1 and S is 1, or when I'm in 0 and S is 1. Okay. Any questions on this? All right.
Actually really convenient.
It is very convenient. Now, it's really FPGAs that made this the way to go. Before we had FPGAs, flip-flops were expensive things. To build a flip-flop, you'll build a flip-flop and it's going to require 7 or 8 gates to build a flip-flop. And so using extra flip-flops was not something people wanted to do. Right? Using the minimum number of flip-flops was important, but on an FPGA, they're already there. There's no point in not using them. All right? And in fact, there's studies, you can go look in the literature, that say that 1-hot actually gives you smaller logic in terms of the combinational logic you need. So 1-hot really works very well for FPGAs. It's very fast and efficient, and because the flip-flops are already there, you're not paying the price of extra logic for it. Plus, that makes your life a lot easier. Okay. Some caveats. Okay. Oh, I do have this. All right, so these are the 1-hot equations we would have for. Notice how much simpler they are. Okay. So when you're making your state machines, there are a few things to be extremely careful about. If you have a state, for each state, you have to make sure that the arcs leaving that state don't have any conflicts. You aren't telling the machine to go to 2 separate states. So if we look at this particular state, we have 3 expressions on the arcs, right? So basically we want to follow this arc when A bar B is 1. And that's these 2 inputs. But if we look at this expression, A or BC bar, that's these 3 cells, the red ones. And so if we're here, we're going to follow 2 arcs. And we're going to end up in 2 states. That's probably not what you want. Okay? So one thing to make sure of is when you make your state machine is that you don't have any overlap. It's not possible for more than 1 arc to be true. Okay? The other important thing, okay, so here we fixed it by basically changing this expression so that we shrank it to this cell. Now there's no overlap. The other important thing is that you can't leave out a value unless you're absolutely 100% positively sure it won't happen. Okay, so in particular, in this case, when A is 1 and B and C are both 0, when A is 1, B is 0, and C is 1, none of these arcs are true. None of these arcs evaluate to 1. So the problem is that in particular in 1-hot, none of your state equations will evaluate to 1, and you will go to all zeros. So if you leave out a particular case, and that happens, your machine is going to go to all zeros, and that's it. Nothing else will happen from then on. Okay, so when you simulate in future labs, you're going to want to put the state bus in the simulator and check that you are only in 1 state, and you are in 1 state. That one of those state bits is high, and no more than one of them is high. Okay. All right. Any questions? Okay. So you'll have, I need to cover this now because you need to know how to do this for Lab 4. At least the 1-hot. Any questions? No? All right, you'll have homework. What?
I said this all
Makes sense? Okay, I'll see you on Wednesday.